Welcome back. In this lecture, we would cover the development of lift on aerofoils and wings. George Cayley in 1785 established from his studies on the flight of birds that a body in flight has four types of forces in equilibrium: the weight and its counter, the lift force, arising out of the interplay of air with the body moving through it, and the aerodynamics, drag, and the thrust required to overcome it. He recognized that heavier than air flight, the problems that need to be solved were the development of wings that have a high lift and low drag and a power source with high power to weight ratio. From his studies on the flight of birds, he showed that it was not possible for a man to fly under his own power by attaching wings. In fact, he was so sure of his thinking that he got a silver medallion etched in 1799 describing what he thought was an essential configuration of an aircraft. This was the first time when an aircraft was thought to have a tail and sail like wings. The idea of a plane surface producing lift is as old as Newton, if not older. Newton proposed a theory for predicting lift and drag on a flat plate held inclined to the incoming air as shown, though he over-predicted the drag and under-predicted the lift. Researchers discovered very quickly that an aerofoil with rounded nose, a long tapering tail, and a curved shape contribute to more efficient wings. Modern aerofoils are highly efficient lifting surfaces, able to generate more lift than similarly sized flat plates of the same area, and able to generate lift with significantly less drag. Aerofoils have potential for use in the design of aircrafts, propellers, rotor blades, wind turbines, hydrofoils, and other applications of aeronautical engineering. This graph shows the development of lift on a thin aerofoil, the aerofoil NACA 0012, which is a symmetric aerofoil with 12% thickness at its maximum. And this is the whole curve for lift for angle of incidence from 0 degrees to 360 degrees, or rather 180 degrees, because it is symmetric after that. You notice that in the beginning, the lift rises very fast with the angle of attack, with the angle of inclination of the aerofoil. This is a very important discovery. In fact, Wright brothers are credited with this discovery when they suspected that the data they were working with was oversimplified and conducted their own experiments, where they found that the lift produced by aerofoils rose sharper than alpha for a flat plate. The rest of the curve, except for this region, the rest of the curve behaves as if it is a flat plate. Not only this, but the drag curve also shows an anomaly at low angles of attack. Notice that the actual drag obtained is very much smaller than the drag that would be obtained on a flat plate. Why is this happening? This is happening because of the rounding of nose. The first picture on the left shows a flat plate. the flow separates right at the nose, producing a thick wake. This thick wake results in comparatively large drag and not so high lift. While the picture on the right is flow about an airfoil in which the nose is rounded, and we see that because of the rounding of nose, the flow does not separate on the top edge. It goes around the body surface, and because of this, it produces a negative pressure on the top, which contributes to increasing lift, the kind of lift we saw in the graph earlier. Most airfoils used in industry are cambered airfoils. Cambered airfoil means the airfoils which are not symmetric but curved. There is a top surface of the airfoil and a bottom surface of the airfoil. The median line between the two surfaces, shown here by a broken line, is called the mean camber line. This is exactly midway between the top surface and the bottom surface. Is a curvature of mean camber line that results in lift even at no angle of attack. A large number of airfoils have been designed and are being continually designed. This picture shows a collection of airfoil shapes. For on the top two, we see the low speed airfoils. A third one is the airfoil for a propeller blade. Supersonic aircrafts have very thin, sharp-edged airfoils. A bird, the wings of the bird are also airfoil shaped. Turbofan blades are airfoil shaped but with sharp leading edge. This is the cross section of the wing of a dragonfly. It's only 12 millimeter long. A sailboat with a sail inflated does also have a shape of an airfoil as is shown in this picture. Typical lift characteristic of an airfoil is shown by this graph. On the horizontal axis is alpha, termed the angle of attack. This is the angle at which the chord of the airfoil is inclined to the oncoming flow. And the lift coefficient, which is defined as the lift force per unit length of the airfoil divided by 1/2 rho v square times the chord of the aircraft, non-dimensional lift. Over quite a bit of range, this is a straight line with almost a constant slope. This constant slope can be predicted by potential flow theory, and we will give a glimpse of this potential flow theory right here. But when the angle of alpha increases, at certain value, the lift coefficient does not rise any further, and we get a CL max value. Clearly, in the linear portion of the graph, the flow is rather smooth over the nose with separation near the tail of the airfoil. But at the peak CL max, as we go beyond it, there is a large scale flow separation on the top surface, which spoils the flow kind of, and we get a large drag. This phenomena is called stall, and the airfoil or the corresponding wing is said to be stalled. A pilot flying an aircraft has to be very careful about not reaching the stall. In fact, the aircraft operates largely within this range of alpha. The typical value of CL max that we obtain varies between 1.2 and 2. There are ways to get a higher CL max, but that is obtained not with plain wings but wings with articulating attachments. And the angle of attack at which such a wing stalls is typically between 10 to 15 degrees. The drag coefficients are surprisingly small. The minimum value of drag is between 0.01 and 0.02, the drag coefficient, which is the non-dimensional drag force, which is non-dimensionalized by the stagnation pressure value 1/2 rho v naught square times the planform area. There is a large range of alpha in which CD is small, and beyond that it rises suddenly. This is when the stall occurs and a large wake results, causing large drag. One of the interesting things to study is the drag polar. It is the polar plot of the lift coefficient and the drag coefficient, CL versus CD. And the curve shape is like this. Beyond CL max, the drag increases very fast. This point here represents the point of the maximum value of CL by CD. People who analyze the performance of aircrafts have determined that when the aircraft flies at an angle of attack such that CL by CD is maximum, it can have a maximum range or maximum endurance depending upon what kind of engine does it have. A glider with no engine has the maximum range from a given height when the CL by CD is maximum. In fact, CL by CD is termed as the aerodynamic efficiency of the airfoil or of the wing. For competition gliders, CL by CD could have values between 70 to 100. That is, they slope downwards at less than 1 degrees. That is, if they start at an altitude of 1,000 meters, they would cover 70 to 100 kilometers in uniform gliding. NACA, the predecessor of NASA, has codified the various airfoils, and this airfoil NACA 23012, which is a 12% thick cambered airfoil, was designed in 1935 at Langley Research Center. It combines high lift, low drag, very mild pitching moment, and even a bit of laminar flow on its lower surface. The curves for 23012 are shown here. It has a stall angle of about 14 degrees, a maximum CL of about 1.4, and a maximum CL by CD of about 75. I had mentioned earlier that the potential flow theory can predict the lift of an aerofoil. Why is that so? Consider the aerofoil as shown on the left. Suppose the flow is not separated, the boundary layer is thin, and within this boundary layer, the viscous stresses cannot be neglected. Outside this boundary layer, in the region called outer flow region, the flow can be treated as inviscid. And this inviscid flow is potential flow with an inner boundary condition that the velocity is tangential at the edge of the boundary layer, right here. But the boundary layer is very thin, and as can be shown in the development of boundary layers, that the pressure across the thickness of the boundary layer does not change, and therefore pressure at the edge of boundary layer is the same as pressure on the surface of the aerofoil. So to predict the pressure on the surface of the aerofoil, we need to calculate the outer flow up till the edge of the boundary layer, and whatever is the pressure profile obtained at the edge of boundary layer can be impressed on the surface of the aerofoil. But the boundary layer is very thin, and if it is thin, to the first order approximation, we can neglect this at all, so that we can treat the outer flow as first approximation to extend right up to the surface of the aerofoil, provided the boundary layer is thin, that is, the flow does not separate. That is, for low angles of attack on a rounded nosed aerofoil. And that is what makes the potential flow theory so powerful in aerodynamics. We can use completely aerodynamic solutions, forget about the no slip condition at the surface of the aerofoil, treat the surface of the aerofoil simply as an impervious body, and calculate the pressures there. To summarize, in streamlined bodies in which the boundary layer is thin over most of its surface, we may extend the inviscid flow up to the surface as a first approximation. This works for lift, but does not work for drag at all. We cannot predict drag. In fact, this predicts drag to be exactly 0, which is obviously not the case. We will have to bring in the viscous effects to predict the drag. While discussing potential flows, we have done flow over a Rankine oval, which was obtained by a source and a sink separated by a distance and immersed in a uniform stream. The pattern of streamline was as shown here, and as was discussed, any streamline can be replaced by a solid surface. This closed streamline, which is shown as a dark oval, now can be replaced by a surface of a body termed as Rankine oval, and the potential due to a source and a sink separated by a distance and superimposed by uniform flow then predicts the flow about the Rankine oval. the potential was written as the potential due to the free stream, due to the source, and due to the sink. Source and sink are situated at x is equal to minus a and x is equal to plus a. Similarly, we could write the stream functions for this. This we had done in the last lecture. We had also done in the last lecture that as the source and sink approach one another, such that as the distance A tends to 0, the source strength Q tends to infinity, such that the product QA remains constant, equal to mu, then we get a doublet. And when a doublet is superposed with a uniform stream, we get a circular streamline. A circular streamline separates the flow inside that streamline with the flow outside. The inside area could be replaced by a cylindrical body, and so this potential function and this stream function give us the flow about a circular cylinder. We discussed this in the last class. We had also calculated the velocity distribution on the surface of the cylinder, and using the surface of the cylinder with this velocity profile, we had calculated the pressure distribution using the Bernoulli equation. If the flow did not separate over this cylindrical surface, then that is exactly the pressure distribution that we will get, or that is approximately the pressure distribution that we will get. But the pressure does separate over a cylinder. It would not separate if the body was streamlined like an airfoil, and in that case the predicted pressure distribution would be the same or very nearly the same as the actual pressure distribution. You notice that in both Rankine body and the circular cylinder, there was a source and a sink of equal strength enclosed within a closed streamline, an oval or a circle. In fact, if we distribute source and sink over a line such that the sum of the sources and sink strengths is equal to 0 over the entire line, then there would be a resulting streamline which would be closed. The problem now is to predict this distribution of sources and sink such that we get a closed streamlines which resemble the shape of an airfoil. For this, it is more convenient to work with a source sheet rather than individual sources and sinks. Consider a source of strength Q. Let's divide this into two parts of Q by 2 and Q by 2. Then we divide this into 4 parts, and then we divide this into 8 parts. And as we increase this division, what we have is a source sheet, a source panel. The advantage of this source panel is that it does not have a singularity like the singularity we had in a source, because the velocity there varied like 1 over r. So as r tends to 0, there was a singularity. On the source panel, there is no singularity of that kind. We define lambda is a function of S to be the source strength per unit length over this source panel. Then d phi, the contribution to velocity potential by a source panel of length ds is lambda ds by twice pi ln r. This is the velocity potential at location r due to this element of length ds of the source panel. We solve a little problem. We assume a flat plate of length L. Let this be a source panel of a uniform source panel strength of lambda. So lambda is no longer a function of x. Let us consider a small element ds at S and then find out what is the potential at point P at the location xy. We write the velocity potential at point P as an integral phi xy is equal to integral from 0 to L of lambda by twice pi ln r ds. Lambda by twice pi ln r ds is a contribution due to length ds. So we integrate over S from 0 to L to get the total contribution to potential at that point. Then we determine the velocity components u and v at any point x and y by differentiating this velocity potential, which we obtained as an integral, with respect to x and with respect to y. And we get these expressions. Now, these integrals are not easy to evaluate, but most often we are not interested in evaluating everywhere. We are interested in evaluating them close to the panel, a distance slightly above the panel and slightly below the panel. And if we do this, then the vertical component of velocity v is obtained as lambda by 2 on a point slightly above the plate and minus lambda by 2 slightly below the plate. So there is a jump of velocity going from below the plate to above the plate, across the plate. There is a jump of velocity equal to lambda, the source panel strength. Now, once we have found out the phi for a source panel, let us immerse this in a free stream, a uniform stream at a velocity v naught, which is inclined at an angle alpha to this plate. So that this plate is now at a positive angle of attack alpha. So we model a constant lambda along the plate. So Vx at y plus, a point slightly above the plate, is lambda by 2 plus V naught sine alpha. The contribution because of the panel plus V naught sine alpha is the contribution to the vertical velocity above the panel because of the uniform stream. And V slightly below the plate would be minus lambda by 2 plus V naught sine alpha. We choose alpha so that the velocity normal to the plate is 0. Now, obviously, this cannot be satisfied both at the top surface and at the bottom surface of this plate, because the normal velocities are different there. So they cannot be, there is only one unknown lambda. So you can't choose lambda such that this condition is satisfied at both the points, a point below the plate and a point above the plate. We now invoke physicality. The flow on the top of this plate would be a separated flow. So potential flow would not apply there. So let this condition be applied to only the bottom of the plate. And if we apply this condition to the bottom of the plate and we make the velocity 0 there, then we can obtain the flow. This is the picture we obtained in which alpha is 90 degrees. The flow separates at the edges, but the rest of the flow region is very well predicted by the potential developed in the last couple of slides. We can, from that potential, determine the horizontal velocity, the only component of velocity present in the bottom of the plate, and that would lead to calculation of pressure along this plate using the Bernoulli equation. And so we can calculate the net force on this plate, which is very close to what we actually get. This would require that lambda is equal to twice V naught. Therefore, phi xy is 0 to L by twice pi ln r dot ds plus V naught x, where lambda is equal to twice V naught, is the velocity potential for this flow normal to the plate, to a finite length of plate. If the angle of attack was not 90 degrees but alpha, then the flow pattern obtained would be something like this, and the lambda would be twice V naught sine alpha to give this flow pattern. The fact that the velocity of the source sheet is smooth is equal to lambda by 2 without the troubling singularity of a point source permits us to use flat plate source panel to model the surface of a 2D closed body. So we extend the use of this source panel to flow about an airfoil or even a circular cylinder. Consider a circular cylinder. We divide this circumference up into a number of panels, flat panels, and for each flat panel, we assume a source strength. Once we assume a strength for this panel, we can calculate the effect of those sources from each of these panels to points at the center of the panels and make the flow velocity tangent. If there are n panels that we use, there would be n control points. So by making the velocity 0, making the tangential velocity 0 at these n control points, we get n equations in n undetermined source strengths. And this system of equations can be solved to get the strength required for each of the panels. We outline here the method applied to airfoil. We take a free stream at a velocity V naught and find out the velocity at a control point here, and we set the tangential velocity 0, and that will give us one equation in n unknown source strengths. This we repeat for every control point So we get n equations in n unknown source strengths. Choose the strength of the source panels such that the velocity normal to each panel vanishes. So we start with the profile of the airfoil. The flow approaches it with the velocity v naught and an angle of attack alpha. We divide the surface of the airfoil into a number of straight source panels, and we choose the midpoints of these control panels as control points. We number the panels and the control point 1, 2, 3, I, J up to M. So there are M panels and M control points we have chosen. We next do the determination of the contribution to the normal velocity of each of the panels at each of the control points. The sum of these velocities plus the contribution of the free stream at each control point is equated to 0, leading to a system of M equations in M unknown source panel strengths. And how do we do this? We calculate the contribution of the ith panel to the velocity potential at the jth control point. That is, we find out del phi ji at the jth control point because of I is equal to lambda I, the strength of the ith panel, divided by twice pi, integration over all i's of ln r ji into dsi, where rji is under the root x minus xj whole square plus y minus yj whole square, where x and y could be xi and yi. The total contribution of all the panels at the jth control point is the summation for all the i's. The total contribution of all panels at the jth control point was obtained as summation I is equal to 1 to m delta I divided by twice pi integral over I, the panel ith panel of ln r ji dsi. The normal component of velocity induced at the jth control point by the source panel is then obtained by taking the derivative of this potential with respect to nj. The above results in a singularity in integration over the jth panel itself, the contribution of which has been evaluated earlier as lambda j by 2. So we eliminate the jth panel from this sum and add lambda j by 2 separately. The boundary condition requiring vanishing of normal components of the velocity of the jth panel becomes lambda j by 2, the contribution of jth panel, plus the contribution of all other panels except I is equal to j, plus the contribution of the free stream V naught cosine beta I should be 0. The normal velocity should be 0. This is a linear equation with m unknown source panel strength. There are a total of m such equations, one for each control points, and these can be solved simultaneously. Now, as was said earlier, that the net source strength for a closed body must be 0. So summation of lambda I over I from 1 to m should be 0. We have not used this equation earlier, so this can be used as an independent check on the accuracy of the calculations performed. Once lambda j's are obtained, we can write the composite stream function and plots its contour to get the streamlines of the flow. To calculate the pressure distribution, we need to know the tangential velocities at the control points, which are obtained from this expression. then the coefficient of pressure at the jth control point is nothing but 1 minus Vj by V naught whole square. This Penel method is used very often, and lots of programs have been developed with this. One such implementation in MATLAB is available at this reference. The viewers are encouraged to visit this site, which is a MATLAB sharing source, and obtain a rather small source Penel method program, which can be used to solve for any closed body. The inside can be replaced by the solid body, and the calculated streamlines are very close to what is obtained. Of course, there is no restriction of alpha on this method. If we use larger alpha, we get a flow like this. We'll expand this. You see here, the stagnation point has moved to a point above the trailing edge of the airfoil. This results in a large acceleration at the trailing edge, a situation which is not physically tenable. You cannot have infinite velocity there. So this breaks down. There is no circulation about a source sheet we have calculated earlier. And so if we calculate the circulation in the flow that we obtain, we will find that circulation is 0, and the lift per unit length of the airfoil obtained would be 0, whatever be the angle of the attack. So this method cannot predict the lift by itself. As we have seen, the trailing edge is this. The flow goes around the trailing edge, acquiring an infinite velocity at the rear point. The stagnation point moves up. So there is flow which is slowing down in this region and in this region. This results in separation. A famous scientist by the name of Kutta produced a theorem which says that the actual flow has a circulation which is non-zero, which predicts a non-zero lift, and that circulation can be predicted. The actual physical circulation in a real flow can be predicted by imposing on this solution a vortex strength such that this stagnation points moves to the trailing edge. As we increase the value of gamma, the circulation, this stagnation point shifts downward. And at one particular value of gamma, this stagnation point is sitting at the trailing edge. And the Kutta condition states that the actual flow is one in which the gamma is exactly equal to the required circulation to make the rear stagnation flow at the trailing edge. To repeat, the aft stagnation point here with zero circulation. I change the value of circulation and this point starts moving down towards the trailing edge. At one specific value of circulation superimposed, that is on the potential flow that we obtained without the circulation, we keep on adding a vortex. And when the vortex strength reaches a certain value, the stagnation point is right at the trailing edge. If I add more of circulation, this stagnation point would move down the bottom surface. A body with a sharp trailing edge which is moving through a fluid will create about itself a circulation of sufficient strength to hold the rear stagnation point at the trailing edge. This is the Kutta condition. So, what we do is we predict the lift by introducing a vortex sheet in much the similar manner as we did with the source sheet. This vortex sheet is now laid along the camber line of the airfoil. The thickness of the airfoil does not contribute to the lift. So, to the first approximation of the flow, we can forget about the thickness and worry only about the camber line. We imagine a vortex sheet of strength gamma s on the camber line, calculate the potential at point xy. Because of this vortex sheet of strength that varies like gamma s, the velocity u on any location s can be determined by differentiating phi with respect to x. There is a discontinuity of y is equal to 0 and we get u, the horizontal velocity, slightly above the camber line as minus gamma by 2 and slightly below as gamma by 2. And this gives us the velocity on the camber line. If the aerofoil is thin, make the camber line a streamline by imposing the condition that the velocity is tangent to it, that is Vs due to vortex sheet at the sheet location is equal and opposite to the vertical component of the free stream velocity. The vertical component of the free stream velocity. So that V naught into alpha plus dy by dx is the vertical velocity predicted by this vortex sheet. Techniques have been developed to obtain gamma s as a Fourier series with Kutta condition that translates to gamma L is equal to 0. With these, we can find out the flow about a cambered airfoil. And the lift on such an airfoil is minus rho free stream velocity times the total sheet strength, vortex strength, gamma. The pressure distribution can be calculated then. This shows the pressure distribution about one cambered airfoil. Thank you very much.